Do you know? Electricity isn't a recent discovery. The ancient Greeks discovered static electricity over 2000 years ago when they observed that amber, when rubbed against fur, could attract small objects. What constitutes electricity? How does electricity flow in an electric circuit? In this chapter, we will try to answer these questions and learn more about electricity. Let's start with the basics. What is electricity? Electricity is a fundamental form of energy, and it's all about the movement of electric charges. But how does it work? Electrons move around and constitute what we call an electric current. These currents flow through special pathways called conductors, usually in the form of wires. So, in essence, electricity is the flow of electrons through these conductors. Electricity is the magical force that makes all of these things possible, like generating light, producing heat, and operating machinery. So, it is a crucial aspect of modern life and technology, with applications ranging from powering homes and appliances to driving electronic devices and industrial processes. What is an electric charge? As the heart of electricity lies the concept of charge, which can be either positive or negative. These charged particles exhibit fascinating behavior. Like charges repel each other, unlike charges attract each other. To quantify this charge, we use the Coulomb, C, as the standard international SI unit. 1 coulomb of charge is equivalent to the charge present on approximately 6 × 10 raised to power 18 electrons. Speaking of electrons, each of them carries a tiny charge, precisely 1.6 times 10 raised to the power minus 19 coulomb. This relationship can be expressed as Q is equal to N times E, where Q represents the total charge, N is the number of electrons, and E signifies the charge on a single electron. Now, let's talk about how these charged particles move, which we call electric current, and the special pathway that allows electrons to travel. We call this pathway an electric circuit. Electric current is essential for technology, safety, and energy distribution. Electric circuits control current flow, influencing electronics, healthcare, transportation, research, and sustainability, shaping our daily lives. What is electric current? Electric current is the flow of electric charge through a conductor, like a wire. It's the movement of tiny particles called electrons along a path. Think of it as the flow of electricity through a wire that powers your devices, like lights and appliances. It can be mathematically defined as I is equal to Q by T, where I is the current, Q is the charge, and T represents time. The SI unit of current is the ampere, A, where 1 ampere signifies 1 coulomb of electrical charge, approximately 6.24 × 10 raised to the power 18 charge carriers, passing a specific point in 1 second. To measure current, we use a device called an ammeter. The symbol for an ammeter looks like the letter A. Ammeters have very low resistance and are always connected in series in a circuit, meaning they're placed in line with the path of current flow. Interestingly, the direction we consider for current is opposite to the actual flow of electrons. When electricity was first discovered, people didn't know about electrons. So, they thought current was the flow of positive charge. That's why we still use this convention today, even though we know it's the electrons moving in the opposite direction. Let us quickly solve a question to see the applications of electric current. Question says, a current of 0.5 amperes is drawn by a filament of an electric bulb for 10 minutes. What is the amount of electric charge that flows through the circuit? Let's solve it together. Current, I, is equal to this is the flow of electric charge through a circuit and is given as 0.5 amperes. Time, T, is equal to the time for which the current flows is 10 minutes, which we need to convert to seconds. So, 10 minutes equals 600 seconds. To calculate the amount of electric charge, Q, that flows through the circuit, we use this formula, Q is equal to I into T. Now, let's plug in the values. Q is equal to 0.5 amperes into 600 seconds is equal to 300 coulomb. So, the amount of electric charge that flows through the circuit is 300 coulomb. The correct answer is say 300 coulomb, as we calculated. Students, did you know that electric potential and potential difference are vital for heart pacemakers, which use controlled electric potentials to regulate irregular heart rhythms, saving lives? Let us now learn about the terms electric potential and potential difference. These concepts are absolutely fundamental in the realm of electricity and electromagnetism, and they play a crucial role in both our theoretical understanding and practical applications. So, let's start by understanding what electric potential is. Imagine you have to carry a tiny, positively charged particle from infinity to a specific point in space. Electric potential, denoted by V, is the amount of work done to move this unit positive charge to that point. Mathematically, it's defined as V is equal to W by Q, where W represents the work done and Q is the charge. Now, remember this, the SI unit of electric potential is the volt, V. Moving on to potential difference, this is the work done to move a unit charge from one point to another. It's represented by the symbol V, just like electric potential. So, you can think of it as the difference in electric potential between 2 points. What's interesting here is that the SI unit of potential difference is also the volt, V. 1 volt is equal to 1 joule per coulomb. So, when we say there's a 1 volt potential difference, it means that 1 joule of work is done to move 1 coulomb of charge between those 2 points. Now, let's introduce an essential tool in understanding these concepts, the voltmeter. It's like a detective for potential difference. Voltmeters have high resistance and are always connected in parallel to the circuit. Current, which represents the flow of electric charge, always flows from a higher potential to a lower potential. It's a bit like water flowing downhill because things naturally move from a higher energy state to a lower one. Let us now learn in detail about electric circuit and circuit diagram. This is a topic that powers the technology all around us, from the lights in our homes to the gadgets we can't live without. First things first, what exactly is an electric circuit? Well, think of it as a closed loop or pathway. It's like a secret passage for electric current to travel through. An electric circuit is a pathway for electric current to flow through various components. Now, speaking of components, what's inside an electric circuit? You'll find wires, switches, resistors, which resist the flow of current, and energy sources like batteries or power supplies. These components work together like a team, making sure the electric current flows smoothly. Now, let's talk about circuit diagrams. A circuit diagram is a graphical representation of an electric circuit. But instead of drawing pictures of wires and batteries, we use special symbols that engineers, technicians, and students all around the world understand. These symbols are standardized, like a secret code for electrical engineers. They make it easier to draw and understand complex circuits. So, when you see a zigzag line, you know it represents a resistor. And when you see 2 lines crossing, it's like a switch. Now, let's take a look at some of these symbols for commonly used components in circuit diagrams. You'll see symbols for cells or batteries, plug keys, electrical components, and connecting wires. These symbols are like the building blocks of electrical drawings, and knowing them is like having the keys to decode the secrets of the circuit. Let us now explore a fundamental law in the world of electricity, known as Ohm's law. Ohm's law states that the potential difference across the 2 points of a metallic conductor is directly proportional to the current passing through the circuit, as long as the temperature remains constant. If we represent potential difference as V and current as I, mathematically, it looks like this: V is directly proportional to I. And we can make it even simpler. V is equal to IR. Here, R is a constant, called resistance. Think of resistance as a kind of roadblock for electric charges. Ohm is the SI unit of resistance, and when we say 1 ohm, it means that if there's a 1 volt potential difference and a 1 ampere current through a circuit, the resistance is 1 ohm. Rheostat is like a dimmer switch for current. You can use it to regulate the flow of electricity without changing the voltage source. Imagine having a magical wand to control the brightness of your room lights. That's what a rheostat does for electric circuits. But what factors affect the resistance of a conductor? Well, there are 4 key factors. Resistance is directly proportional to the length of the conductor. Length: the longer the path, the more resistance it offers. Area of cross-section: resistance is inversely proportional to the area of cross-section. Think of it like a highway. The wider the road, the easier it is for cars to flow through. Temperature: resistance is directly proportional to temperature. When things heat up, electrons get a bit jumpy, making it harder for them to flow smoothly. Nature of material: different materials have different resistances. Now, let's talk about something called resistivity. It's a measure of how much a material resists the flow of electricity. Resistivity is measured in ohmmeters and doesn't change with the material's length or cross-sectional area, but it does change with temperature. Metals and alloys have a relatively low resistivity, which makes them great for conducting electricity. That's why you'll often find copper and aluminum in electrical transmission lines. Alloys, in particular, are fantastic because they don't burn easily at high temperatures, making them perfect for electrical heating devices. What happens when we connect resistors in different ways, in series and in parallel? First, let's talk about resistors in series. When we connect 2 or more resistors end to end, it's called a series combination. Total resistance in series. To find the total resistance in a series combination, you simply add up the resistances of all the individual resistors. So, resistance in series is equal to R1 plus R2 plus R3. What's cool here is that the current flowing through each resistor is the same. But the voltage across each resistor can be different, depending on its resistance. To find the voltage across each resistor, you can use V is equal to I into R. The total voltage across the entire series is just the sum of the voltage drops across each resistor. So, V is equal to V1 plus V2 plus V3. The equivalent resistance in a series combination is larger than the largest individual resistance. Talking about resistors in parallel. When we connect multiple resistors in parallel, both ends of each resistor are connected to the same 2 points, forming multiple paths for current flow. In this case, the voltage across each resistor is the same and equal to the applied voltage. The total current is the sum of the currents through the individual resistors. So, I is equal to I1 plus I2 plus I3. The equivalent resistance in a parallel combination is less than the value of the smallest individual resistance in the combination. To find Rp, you use this equation. 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Advantages of parallel combination. In a series circuit, if one component fails, the circuit is broken, and nothing works. In parallel, if one device fails, the others can still function. Different appliances have different current requirements. Parallel circuits allow us to power devices with various current needs. The total resistance in a parallel circuit is decreased, which means current can flow more easily. Students, let's now discover how electricity can warm up our world in various ways. What is the heating effect of electric current? Well, when an electric circuit is purely resistive, all the energy from the source gets transformed into heat. It's like turning on an electric stove, and the heat generated is precisely what we're talking about here. Mathematically, we can express this as E is equal to P times T. Here, E represents the heat produced, which we'll call H, P is the power, T is the time, V is the voltage, I is the current, and R is the resistance. So, we can write it as H is equal to V into I into T, or H is equal to I square R into T. Now, let's dive into some practical applications of this heating effect. Joule's law. Joule's law tells us how the heat produced in a resistor depends on various factors. It states that heat produced is directly proportional to the square of the current, directly proportional to resistance, and directly proportional to the time for which the current flows. The heating effect is desirable in devices like electric heaters, electric irons, and electric bulbs because they're designed to produce heat. But it's undesirable in devices like computers, monitors, TV, and refrigerators because we don't want them heating up. In electric bulbs, most of the power consumed turns into heat, with only a small part radiated as light. That's why they get warm when they're on. These bulbs use tungsten filaments because tungsten doesn't oxidize readily at high temperatures and has a high melting point. Electric fuses are like the protectors of our electrical appliances. They're made of pure tin or copper tin alloys, always connected in series with a live wire, and have a low melting point. If there's a short circuit or overloading, the fuse melts and breaks the circuit to prevent damage. Now, let's talk about electric power. This is the rate at which electric energy is consumed or dissipated in an electric circuit. Power formula. You can calculate power using the formula P is equal to V into I, which also equals I square R or V square by R. The SI unit of power is the watt, W, and 1 watt equals 1 volt into 1 ampere. We measure the consumption of electric energy in kilowatt hours, kWh. So, 1 kWh is equal to 3.6 times 10 raised to the power 6 joules, or simply 1 unit of electric energy. In this chapter, dear students, we have delved into various fundamental concepts related to electricity. We began by gaining a comprehensive understanding of what electricity is. We examined the concept of electric current and its role in electrical circuits. We explored the notions of electric potential and potential difference and how they relate to electrical energy. We learned how to represent electrical circuits using schematic diagrams for better visualization. We awared ourselves with the symbols used to represent commonly used components within circuits. We studied Ohm's law, which relates voltage, current, and resistance in electrical circuits. We investigated the factors that influence the resistance of a conductor in an electrical circuit. Lastly, we explored practical applications of the heating effect generated by electric current in various real-world scenarios.